Record. All right. And so you're asking about number 4 from the practice test.
Right.
Okay.
Part of what confused me was expressing the answer in the right terms.
Oh. Okay. Let me come back and read it, and then I'll kind of try sharing my camera screen here again. It says uses Gauss's law. Oh, find the electric field in terms of A and lambda. Now I'm a little confused at this point what A might be. Usually it's the radius. Oh, I see the picture. The photocopy is hard to see, but it is there. Okay, so A is the radius of it. Okay, and then it's two-part question, both inside and outside of an infinitely long, uniformly charged cylinder of radius, oh, there it says it, A, and of charge per length, lambda. And did it say uniform in there? Oh, good. And it said infinitely long? Good. And then B, there's a B part of this, the flux, through the sphere surrounding this dipole. Okay, let me start with A. I think that was your main question, but I'll do all of the above. Let me see, now that I rebooted everything from this morning, I'm cautiously optimistic that if I click on share, yes, it will go to my computer. Good. Yes. I mean my camera, my phone, and they're looking good. All right. No good. That popped up. Nice. Then if I go to my camera, nice, and zoom in a little bit. Oh, maybe that's a good zoom right there. Nice. All right. Oh, yeah, much clearer, much better than this morning. I wish I knew exactly what it was, because I think it's a combination of the network. I rebooted it, but also the quality of my screen here. All right. Well, anyways. All right, Gina. So I'll start from the beginning here. So this would be number 4 from the practice test. And to kind of match their picture, I'm going to make a cylinder that kind of goes up at an angle. And, oh, wait a minute. I'm going to do a stopwatch here. Nice. Be a little bit off, but it looks like my wife just brought me an iPad that's got a stopwatch. Okay, good. Kind of overkill for an iPad, but that's nice. All right, so I can do timestamps a little better. All right, so back to this problem here. So I've got this cylinder of radius A, and it says both inside and outside. So the picture shows a Gaussian surface on the outside. So let's go ahead and do that one first. And then starting with Gauss's law, if we take a closed Gaussian surface and integrate over it, so that's the left-hand side of the equation, and set that equal to the charge inside over epsilon naught, and I don't know why I wrote it as 2 pieces. Usually we see it this way, so I'll kind of make it look the way you normally see it. Oh, and I'll label page 1 in case you've got to jump back and forth. Then this Gaussian surface that I'll just make length L for it. And of course, like you saw in the homework, and I'll maybe do the dot product kind of quickly unless you have a question, but it kind of got the impression that that wasn't your concern. It was really more towards the end, writing in terms of those variables. And so I'm going to put then the electric field on the outside, because again, the symmetry argument is that anywhere on this Gaussian surface, the charge would look like the same distribution, therefore it must give you the same electric field, regardless of where you are on it. So we can take that out of the integral. And of course, the other symmetry argument is that since it's a line of symmetry, it must be along the same direction as the normal, which makes that 0 degrees. And so this just becomes E times the area where the area is, and it would be kind of this wrap around if I used maybe a sticky pad again here. Don't even cut it in half. But if this pencil, if I hold it up, represents my charged cylinder, then I am wrapping around it kind of like this Gaussian surface. Actually, it probably would have been better to not fold it in half and use the sticky on the. Okay, so here's the idea of the Gaussian surface. But what I'm trying to point out then is the surface would be this yellow piece of paper. And so if you unfold it and say, well, what is the area of this? Well, it's the, I'll call this the width, but it would, when it's rolled up, that's the circumference. So this would be 2 pi r. And then of course, when it's rolled up, this would be this length L here in the picture. So there's the calculation on the left-hand side. And correct me if I'm wrong, but I got the impression that that really wasn't the meat of your question. You've seen that and you were good with that. Now, the other side of this is actually a problem that we were just doing the best we could at the end of the first session, because number 5, you had to figure out the total charge, and that's what this would have to be. And I think that's really kind of maybe where your question really lies. So let me come over to the right-hand side. I'll use the 1 over epsilon naught and leave that alone. But I would then write that the total charge then that is inside of the Gaussian surface is this integral. And this integral means add up all the little chunks of charges that are in here. So if you were kind of thinking of this cylinder then as slices, and so maybe this long cylinder is maybe more like a roll of quarters, and each little slice is a quarter, and then of course there's a certain amount of charge per unit length there. That's what the lambda stands for. It says how much charge is on one of those quarters divided by the length of the quarter. Or usually we held a quarter in our hand, we'd probably call that the thickness. But since I have this laid out, I will call this direction going back the x-axis. And so that would be the charge per length. So using this and doing a substitution for dq, I would get an integral of lambda dx for the charge inside. And then, of course, the lambda is uniform, meaning it's a number. And so then we just get an integral of dx, and we would just add from 0 to L. And so this right-hand side of the equation would become lambda L over epsilon naught. And in fact, now that we've done these integrals a few times, let me point out that anytime you have a uniform charge distribution, you're always going to get this effect where the constant pulls out, and so you can just measure it by the density times, in this case, it's length. If this was a volume, this would be a rho times the volume. And you're always going to get that if you have a uniform or a constant density. And so that's what we have here. And so that's the idea here. Now, continuing on, the L's would cancel off, and we would get a formula that you've seen a couple of times on the homework, and maybe it's getting to the point that you've maybe even memorized it, but this is the electric field from a line of charge, and then the lambda is a line of charge. When we first derived this, we derived it for something that didn't even have a size A. But as you can see, the size A wouldn't really even come into play for this calculation. Now remember, of course, I'm talking about this is the electric field outside of it. A is going to come into play for the second part of this because the problem says both inside and outside. So anyway, this is, I think, where we can stop. We can't really put in a number because we're not told the lambda. So, and we're not told where to get the field. And so this would be value any place where R is greater than A. And technically it would be equal to A. And so I would say we've done the first half of part A. We have found the electric field on the outside. And so that's what the R greater than A means. So let me try all this again, page 2. But this time, when I draw the charged cylinder, oops, that's off the screen. Oh, I gotta turn off all these notices. They keep popping up, huh? All right. But if I have a charge cylinder of, A and charge density lambda, and at this time, if I draw a Gaussian surface, maybe it'll stand out, I'll draw it in red. Oh yeah, I still want to get a bunch of colored pencils or pens. I'm gonna do that. Got to make that a goal here. I just got these 2. Okay, but the Gaussian surface now, which I'll label as radius R, is actually inside. So when I start off with Gauss's law again, the left-hand side of the equation actually doesn't change. So unless you have a specific question, I'll just put that result that we got over here. I would, still be taking this Gaussian surface and making a cylinder out of it. Although you might argue it would be a little smaller radius Gaussian surface because now it has to be a value of R less than A. So I'll wrap my sticky a little tighter, but that's what it would look like here. But the math would come out the same. So this is going to be E 2 pi R L when we have the electric field and the area. And so all these steps on page 1 are identical. Okay. What changes though is over here on step 2. Oh, and maybe this is the heart of your question, because now I can see the challenge here. Yeah, I didn't see this coming. But over here, we need to be really careful, because if you remember my discussion back here and saying, okay, these are quarters, and the charge, on each quarter divided by the width of that quarter would be length, because that's what lambda means, the charge on the cylinder, and the quarters represent the whole cylinder. But charge inside would actually be little slices like this. Maybe for an analogy, if my charged sphere were the 25-cent pieces, the quarters, this is something smaller like a dime. And so it's technically the charge per unit length on the dime times its length. And that is not the lambda. The lambda is the total charge on a quarter. So I've got a little bit of a challenge here of saying, okay, now how am I going to do this? So let me do this. Let me at least put in my equation the words I just said, that this would be a charge per length, a dq over a dx. But unlike back here, I'm not talking about the charge on the whole quarter, and therefore this is the whole charge per length. This is some smaller amount, like a dime size. So maybe I'm going to do this. I'm going to put a little prime here and say, so this is the charge per length on the dime. And then, of course, this would be the charge on the dime. Now, the reason I wanted to write it out then is I could write this as lambda prime dx still, and end up with a lambda prime, and then this integral would be from 0 to L over epsilon naught, and then it would be an E over 2 pi R L. And so, again, looking at R greater than A, this is, so far, I would say it's the same thing. The big rub, though, and now I think this was the heart of your question, is the big rub is this lambda would be different than that lambda, because this lambda in part one is the charge on something the size of a quarter, the whole rod, the whole cylinder. But this is the charge per length on something a little smaller in size. So let me pause with this equation. I'll put a box around it, but I'm going to pause to say, now, how would I figure out this lambda prime? And I might do something like this. If I would look at, and for lack of better symbolism, I'll put a quarter here. And I would look at a cylinder that was the size of a dime. What would be the same about them is not their charge per length, but their charge per volume. In other words, the quarter, if you took the charge on the quarter, call it D, well, let me back up a step. Let me say rho would equal to rho. And so one little cube, if I took a little tiny cube in here, I mean, my picture is so small, it's kind of hard to draw a small cube. But if I draw a small cube in there, that charge per volume of that cube would be exactly the same as the charge per volume in one that has a smaller radius. And so maybe the way to answer this is to do something like this, that if I call this then a little bit of charge that's on that cube, and I divide it by a little bit of area, okay? No, I don't like that. I think I'm going to confuse you more. Shoot. Okay, forget that. No, don't like the direction I was going. That's going to make it hard in a couple steps. Okay, let me try something a little different. Let me just go to a clean page here. I'm going to pull this one aside. I guess what I'm trying to say here is, if I started with what lambda is, let's see if this direction looks a little better, which would be the charge on a quarter size piece divided by its length. You see, in a quarter piece, the charge on a quarter would be the density leave the dx there, times the volume of a quarter. And the volume of a quarter would be pi a squared dx. Okay, I think I like this a little better. Now, it may not be obvious quite yet, but I'm going to take and multiply the top by an r squared and the bottom by an r squared. And the reason for that is this r is supposed to represent the radius. Yeah, I think I like this better. You can tell me if this works for you, Gina. But this r would be then, coming back to the picture, representing the radius of my Gaussian surface. So this is the dime-shaped piece. So if I were to take the pi and the r squared, that would be the area of a dime. If I multiply that by the dx, that's the volume of the dime. And if I were to multiply that by the rho, that would be the charge on the dime. So these four are the charge on the dime, just like these four were the charge on the quarter. Of course, I was using the radius of the whole thing to get the charge on a quarter-sized piece. Here, then, I would be using the r of the dime. All right, so these four become the charge on the dime, and then when I divide it by that, that now becomes the charge density on the dime, and then I have the a squared over the r squared. And I think maybe that was the heart of the problem that you were getting at, is to finish this problem, it says to write it in terms of lambda. So we need a connection between lambda prime, that is the charge on a dime-sized piece, compared to the charge on a quarter piece. And this is that numerical calculation. In fact, I'll just rewrite it then as lambda prime equals to lambda r squared over a squared, because that's really what I need. So let me come back to page 2. So on page 2, and I get rid of that thing, but we had this equation. And so let me continue on with it. E equals, in fact, maybe I'll just continue on with it on page 3. Why don't I do that? So let me just recopy that equation from page 2. So this is E, so I'm looking for the electric field, 2 pi r L, and then there's the lambda prime, and then there's the L over the epsilon. I could have canceled the L's earlier. I didn't, but I should have. But there's the magical step right here. So this would be a lambda r squared over an a squared right there. That's the, I think, the heart of this question. Oh, and then let me not forget the epsilon naught there. And then this is the E over 2 pi r. And then there's an r on each side. So to solve this second part of the problem, or second part of A, here's a part B also. I could write this as a 1 over 2 pi epsilon naught, like it looked before. I could write it as a lambda. But now I would have an R upstairs and an A downstairs. And so this would be the equation for the electric field if R was less than, and even equal to, because everything I said would have been valid at the boundary. And so here are, I guess, our two answers. If I go back to page 1, this is the equation when you're outside of the cylinder. This is inside the cylinder, and you can see they're both valid at the boundary where R equals to A. And sure enough, if you put an A into here, you put an A into here, it would cancel with that, and these would be the same answer. So I don't know if we would want to plot them. They were not asked to. So during a test, I'd say I don't bother to plot them. But maybe to complete our understanding, it looks like for r less than a, the electric field is 0 in the center and grows until it gets to a. So it would follow this equation. That's a linear growth. Then once it gets outside, it would follow this equation, which would be a hyperbola decay. So we have a linear growth and a hyperbola decay as a plot of the electric field inside and outside. Now, that was an interesting one. Glad I did that one. And that's, I'm sure there's other ways. I should look at the solutions of how the author might have gotten a connection between the charge per length on the cylinders. That was just kind of what came to me second. I tried the first time. I didn't like that one. Now I'll continue on. I don't think you were really asking about B, but maybe just for completeness. This is kind of the heart of Gauss's law. And so B here would say something like this. It says, what is the flux through the sphere? So the sphere is a closed surface. And flux is this integral of dA. So you really are asking for the flux through a closed surface. And Gauss's law says that would be equal to the charge inside divided by epsilon naught. Now the key to this is that it's a dipole. And so a dipole means you have one of them of the charge Q and the other one is the opposite of that. And so it comes out to be 0. And so the flux would be 0. If you drew a picture, if this is the positive one, you would have flux coming out. And if this is the negative one, you would have flux coming in. And these guys, some of them would not even go through the surface of the sphere. Oh, I didn't draw a very good sphere. Some of them would actually exit the sphere, but then re-enter. But hopefully in this picture, you can see everything that goes out has a matching one of everything goes in. So coming out are positive flux, going in are negative flux. And that's what this means, positive and negative. Let me get you the kind of the same thing there. Nice.
Oh, Dr. Young, I think your feed is frozen.
Oh, has it been frozen long?
No, just in the past 30 seconds.
Oh, okay. Yeah, it looks like it lost connection. It's asking me to connect again. Okay. Okay, so if it just froze in the last 30 seconds here again, you probably got the picture. And what I was trying to say here then is that visually you can see flux comes out, that's positive, and it's matched by flux going in. In my picture, I've got 1, 2, 3, 4, 5 going in, and 1, 2, 3, 4, 5 coming out. These don't go in or out. So 5 out and 5 in. So a plus 5 and a negative 5 gives me a total of 0 flux. So, did that help?
Cool. Yeah.
Okay.
The energy inside the cylinder gave me trouble.
Wait, whoa. Did you say energy?
Oh, part A, sorry.
Part A. Okay, so the E is electric field.
Right, excuse me.
Yeah, okay, so the electric field. Go on now. Continue on with your question. I didn't mean to rudely interrupt you, but I didn't want you to miscommunicate.
Right, thank you. Yeah, I'll just have to review it. The fact that the question wants the answer expressed in certain units can be difficult for me to substitute. Rearrange.
Right. I do see that. And this wasn't easy, but I guess I hope that at least A was easier than B to you, because
right.
A was outside. Yeah, and then you could just use the lambda they gave. But once you start talking about the inside piece here, which was this kind of picture here, where I said, oh, now we're talking about and I called it lambda prime. And know this, I should say this for you and everybody else listening to this, that this would have certainly have gotten you a lot of points on it. You didn't technically completely answer it because it says the quantities given, which were lambda. But if you gave it in terms of a lambda prime, that would tell me a lot. It would tell me you're thinking the same thing. It would, in the sense that inside and outside. It would tell me you also notice that the charge density for the inside piece is a lot lower, or certainly different than the outside piece. And if you didn't make what I'll call the hardest step, where was it, right here on page 3, the connection between the lambda and what I called the lambda prime, that's certainly not the end of the world. If that's all you missed, that's actually still, I probably would just take off 3 for that. It's a major concept, but it's 17 out of 20 for the problem. It's like, okay, they knew it was Gauss's law. They knew how to get the charge on the inside. They knew it was on the outside. They did the other parts all right. This is an important part, but one they just couldn't quite close it on, but still did a really good job on it. So
Cool. Thanks, Dr. Young. And then if you'll let me ask this,
yeah, go ahead.
I noticed you made the exam open notes, an open book.
Yes.
I was wondering if that would impact the difficulty. Do you think the practice test is still a good indication of difficulty to expect?
Yeah, I know this, everything's new to you and me for this online learning. So my goal is to still get you guys to that same level, not to make it a harder level. Admittedly, the open notes and the open books kind of makes it a little bit easier, but everything else we're doing this semester makes it a little bit harder. So in my mind, I'm kind of thinking that balances off. So I'm, if you know this material, to that level, I think, for your own sake, forgetting the grade part of it, but for your own sake, you know it and you're ready to move on to, your next set of classes, which is when you transfer. So that's, yeah. So I'm shooting the same level. And these are hard. I mean, if you've done these, and it sounds like you've done it 1 through 4 at least, but maybe you've gone 4, or maybe you started on number 4. You'll notice they're not easy. Yeah.
Okay.
Yeah. Now, oh, by the way, as long as you bring that up, you'll probably notice like this 4A, the one that said outside, with an open book and open note, you could really just turn to chapter 24 and look that one up. It was done as an example. I realize that, but the other part of this on the inside, writing it in terms of lambda prime, a lambda by using the lambda prime, I'm not sure if that one's in the book anywhere. And so, open notes, open book, only goes so far, really,
Okay.
Yeah.
Thank you.
Yeah. But yeah, to hopefully alleviate your fears and anybody else's is, no, these are hard enough. I'm not going to say, oh, you have it easy now. And to, I gave that some thought because I think other instructors have done it, and I've heard students say that. But unless I was also giving you more time on the test, and that's what I'm not doing, then, I don't think I would do that. So anyway, that's my thinking.
Yeah, plus virtual learning has posed some challenges as well.
Yeah. Oh, yeah, absolutely. Yeah, absolutely. Yeah. And yeah, there also are some goods too, but at this point, this direct face-to-face, and if I was sitting here in the lab this Friday afternoon with you on the board, it would be much easier for us to communicate and pick out your holes. So yes, this is harder to learn for you. So
Yeah. All right.
that's what I really liked about the Friday thing. I can have, all you guys who are in there, I can see, your face, your reaction, your body language, and I can tell, are you getting it or are you not getting it? Wait, let me stop right here. Or you could then just work on it and come back in 20 minutes. Okay, it's this step that's driving me crazy. Why did you do this?
Dr. Young, do you think we
Yeah.
should place more emphasis on lecture examples than homework for exams style problems? That's the way Doug had us study a little bit.
Yeah, I don't know if I'd say that. I don't know if one is better than the other. I think that because it does vary from chapter to chapter. A lot of the examples in the chapters are kind of your first step. So they're trying to teach you the basics at first. So they don't really get to the meat of things. And that's where the homework problems come in.
Oh,
So,
okay.
yeah, so some of the examples can be just a little too plug and chug. But that's not a fair statement either, because they start off with easy examples, that's true. But by the time they get to the end of the chapter and they're putting everything together, there's some real hard ones. So I think they're both really good. I guess I would say it this way, that they're like this problem here in number 4, you will probably see, part of the problem or part of the problems really be the same as the examples or the homework. But then you'll see a part B that will be something that was like, oh, wow, I don't recall doing that problem exactly. Like 4B, I don't know if we did a problem exactly like this, although there were some questions on the homework about what's the flux through a given surface. And so if you had done the homework, even though I don't think there was a dipole one on the homework, in fact, one of the examples in the book and the ones I did in the lecture had like this cube and had a bunch of charges inside of the cube. And so that was an interesting one in itself, but the idea was that the total flux would be the sum of the charges inside. And so once you see that, even though this problem is not a cube, it's a sphere, the idea is that you would connect those two together. That's where, I guess, advanced thinking comes into play, where you're not just repeating back what was lectured at you, but you actually took the concept and did something that wasn't exactly the same, just had the same principles.
Okay. And then you mentioned this earlier, that there was a technical problem in session 1. Does that mean
Yeah,
you won't be
session
able to
1,
upload?
my camera kept having troubles. I'll still upload the video.
Oh, okay.
Because it'll be kind of choppy, I think, but at least you could, maybe fast forward it. I'm hoping the audio, usually when it gets choppy like that, the video gets choppy, the audio still comes out clean, and then the video, you could just, wait till it gets to a place and you could hit pause and instead of watch me write it, because the audio and the video got out of sync.
Okay.
But I definitely think it's worth seeing and worth posting. Mm-hmm. But with that being said, I have no problems doing another one from this chapter. I mean, no, I guess it's a problem set. All right, well, let me switch back over here. Let's see how many, I got 6 here in the room. Let me turn on the chat. How do I get back to the chat? All right, so I'll just go into the next who shot this at me. Oh, Daniel, okay. When you could chance, can you go over practice number 7? Well, absolutely. All right, let me clean off my.
Actually ended up figuring that out.
Sorry, you figured it out?
Yeah, so
Nice.
I was having trouble solving the integral, but because my numbers weren't matching their like the numbers they had at first. But what they did was they changed the dimensions into the U world, where I just left it in the X world, and solved it that way. So it ended up coming out the same. So.
Oh, good. Okay. Okay. So I'll pass on that one. And now let me take this as an opportunity. And then Gina, hopefully you're still listening in there. Is that Daniel? I don't know how you did your integral. I don't know if you actually worked it out like in a math class, or this is what I want to say. Remember, Appendix B is a very powerful appendix there in the survey book. And as I said, if this was a face-to-face meeting and a face-to-face test and we're in the classroom, if this was just an integral that involved a U sub or a power function, I kind of expect you to be able to do that. But those trig subs or some of the harder ones, I would give you. In this case, I guess I need to think about this. Should I give it to you, or should I just say, I don't think I'll bother to type it out. I'll just say, since it's open book, you might want to check the integrals in Appendix B.
That's what I did. I figured since it is open book.
Yeah, and that's what I wanted to encourage you. I don't know how hard that integral is, if it does, but if it's harder than a U sub, yeah, definitely, especially on a time test. Because
you could do it with a U sub, but it would definitely take a few steps to do.
Okay.
So.
All right.
Yeah, it was y over it was y dy over 3/2 x squared plus y squared. Which is a doable integral. It's just like you said, on a time test, not the easiest thing to do.
Yeah. And that's why I do that, because I don't want the test to be a test of your calculus skills, although you should know your calculus skills. I get that. But that's what the homework's for. You got a lot more time. You're not under a time pressure. Well, I say that laughingly because I think we all are under time pressures and all have very little time, but you don't have an immediate due date yet. All right, anybody else out there? I don't see any in the chat room. Yeah.
No one has a question. I'm working through question 8 at the moment.
Okay.
I'm struggling with a little bit, if no one else has one.
Okay. Sounds good. Let's jump on number 8. Okay, so number 8. Oh, and let me write this on my little notes here. Number 8, and I even got a time stamp. Looks like about 40 minutes. We didn't start this quite right, so I'm sure it's off a little bit, but I call that good. All right, and let me look up number 8. So number 8 says this. Oh, what is the charge and the voltage on each of them? Ah, good. Let me redraw that picture here, because this is, well, hopefully the heart of the concept is here, that you've got to recognize whether they are hooked in series or in parallel.
Yeah.
And the first step I would do would be look at these two, number 3 and number 4, that are labeled there, and say, okay, these two are in series. That is, you can see that there's a wire that just goes straight from one to another. And that's kind of this magical step. You've got a wire that goes straight from one to another. That is the definition of a series. So leaving capacitor 1 and capacitor 2 alone for a moment, I am going to replace these two capacitors, 3 and 4, with its equivalent. So I think I'll write it as capacitor 3, 4. Maybe I should put a comma, otherwise it looks like capacitor number 34. And I could even do a calculation. And since they are in series, we do a reciprocal calculation. And so this is 1 over, and so this is a 20 microfarad, and number 4 is a 10 microfarad. And as I was trying to show you guys on the lab video, and I'll show you again here, take advantage of the reciprocal key. So you can just write 20 and then hit reciprocal for your first term, and then say plus.
There's a reciprocal key for the TI-36X Pro, because that's, I was looking for that, but wasn't seeing it, so.
Oh, I'm not familiar with that model, so.
It's, hold on. Let me.
But I bet it has it.
I mean, it's a TI scientific calculator, so.
Yeah.
I was looking for it. I mean, it's just an extra step, just if you knew, but.
Yeah. So in your case, if you can't find it, just do it this way. I'll do it the other way too. I'll just go 1 then divided by 20 plus 1 divided by 10. So you just got to hit divide. So there's not too much in there. But here's where the reciprocal key is nice at the end. Then you got that answer, and that's what they add up to. And so to get the reciprocal of that, so you can get it back to the equivalent, you can just hit the reciprocal key. And so that's where this 6.67 microfarads comes into play here. All right. So that would kind of be my first step, and say, okay, what is the equivalent capacitance of 3 and 4? Then I would look again and say, all right, this one here is the equivalent of that one. But is there anything that's equivalent of this equivalent? So I like to say, is there an equivalent to the equivalent? And of course, this capacitor number 2 and capacitor number 3 are in parallel.
And you can do the just regular right side up addition with that, right?
Since a wire has the same potential, the definition of something being in parallel is that they have the same voltage difference between them. So if there's no connection, if there's nothing between the connection between the two top plates, and also nothing between the bottom plate, that means the top plates would be at the same potential and the bottom ones would be at the same potential. So the difference between...
So after the voltage goes through that first capacitor, then whatever's left after will go through that split stuff.
Yeah, now, yeah, I like what you said. Your concept was good. But the way you said after the voltage goes, you're making it sound like the voltage travels.
Yeah.
And the voltage doesn't travel. The voltage is an energy level. So a better analogy, if this was physics 121, would be to say that, if I had this really tall building, then, partway down in the building is a change in the potential energy, and the other partway down is the other change in the potential energy. But the energy doesn't.
Isn't it the pressure?
Energy's not moving down.
Mm-hmm.
Okay, and you could think of it as pressure, but again, if this was the ocean, if you will, partway down there's a change in pressure, and then the other partway down there's another change in pressure, and yes, the total of those two adds up to the change in pressure on the whole ocean. But I wouldn't say the pressure flows down the ocean.
Okay.
But
yeah, that's miswording on my part.
Yeah. So I know it's not so much the wording. I just want to make sure the mental picture you have in your head is straight, because we are about to get into currents, And current is what actually then does flow. And so in the ocean, what actually flows is the water. There is something that actually flows. That's called the current. Those are the charges that flow. And so we don't want to miss what actually is moving and flowing versus a difference, as you said, a pressure difference, a push, if you will.
Yeah, just the way, and I guess it's from my auto classes, just the way we learned it there was amps is current, and then volts is pressure.
Okay, good. And right. But again, like a hose, if you have pressure in your hose, you don't say the pressure flows. It's the water that flows.
Yeah, that makes sense. Cool.
The pressure is what pushes the water. So your analogy that you're saying in your auto class is great. Just again, you would never say pressure flows. So we would never say voltage flows. Okay, so all right. So actually, then of course, then you're probably well experienced then with series and parallel, and so you might not even need my little discussion here about recognizing how they are hooked up. But these are definitely in parallel, right? This would be the like two headlights on the car. You know, you would want to hook the wire to one side of the headlight left and one side of headlight right. All right, but so this then I will call the equivalent of number 2 and number 3 and number 4. And since these two are in parallel, you add them together. And this is the 10 microfarad. So 10 plus 6.67 would be 16.67.
Okay.
And so I guess I would call this the equivalent of the equivalent. And if I could even make it easier on myself, I would ask one more question. Are these two in either a series or a parallel? And again, our definition of series is when it goes from one and straight to the other without, some other wire connecting. And, so it goes from one to the other. There's no other place for it to go. And so, yeah, those are in series. So ultimately, I would have, if I call this the equivalent of the equivalent of the equivalent, this would be the equivalent of 1 and 2 and 3 and 4 all combined together. And of course, since they're in series, I have to do this reciprocal sum. And so number 1 here, which is the 15, so I'll take the reciprocal of the 15 and also the reciprocal of the 16.67, and eventually then get the equivalent of all 4 of those. And so this is what I call the first half, maybe even the harder half, I don't know. But the first half is really, can you take something as complicated as 4 capacitors and make it equivalent to 1? And so if I grab my calculator, I'll do your method. So 1 divided by 15 plus 1 divided by 16.67. And then take the reciprocal of that. So 1 divided by the answer is how you would do it if you didn't have a reciprocal key. And I come up with 7 points, it looks like it rounds up to 90 microfarads for this, what I'll call the final equivalent capacitor, the equivalent of the equivalent of the equivalent. Now, the reason I say that is the magical connection here is because then we can work with this equivalent of the equivalent of the equivalent really easy. And of course, that only helps us if there's something about this equivalent of the equivalent of the equivalent as it helps us back to get to the real circuit. Because we want to solve the real circuit, and that's what the problem is. The problem is saying, could you give me the charge and the voltage on each of these individually? And so what I've done is a bunch of equivalencies, but I want to point out the equivalencies are just a tool in order to figure out the real answer. But it's a very powerful tool. And so I will come over here to page 2 and say, all right, if I made a little chart, here's capacitor 1, here's capacitor 2, here's capacitor 3, here's capacitor 4. Maybe I should put their value. This was, number 1 was a 15 microfarad. Number 2 was a 10 microfarad capacitor. Number 3 was a 20 microfarad capacitor. And number 4 is also a 10. All right. And so if I had a little chart here that says, well, what is the charge and what is the voltage? So I want to fill in this little chart, the charge on voltage on each of these. But I claim that coming back here to this equivalent of the equivalent actually does help me in my real circuits. I'll show that in just a second, but let me come back to this equivalent, because if I wanted to know the charge on this equivalent 1, 2, 3, 4 capacitor, remembering that, maybe I'll write it up here, that capacitance is charge over the voltage. If I take the capacitance and multiply by the voltage, so 1, 2, 3, and 4. So if I have the equivalent capacitance of all of them, 1, 2, 3, and 4, and I multiply by the voltage, I would get the charge on it. Now, that's where this equivalent of the equivalent of the equivalent really is powerful, because this equivalent one capacitor, all of it is hooked to this one battery. And this one battery is a 20 volt battery. So I could just take this 7.90 microfarads and multiply it by the 20 volts. And that would give me the charge. So 7.9 times 20.
That's the total charge of the whole system, right?
Well, okay, so let me talk about that, but let me just do this calculation. Okay, so this is 158, and I'll leave the micro alone. So there's the micro, and remember, a farad is a coulomb per volt, so that volt would cancel with the one from the 20 volt battery, and so there is the charge. As you said, I don't want to say the whole thing quite yet. I want to be careful with that phrase, but I'm just going to come back to the equivalent of the equivalent of the equivalent. What this is telling me is there would be a charge of 158 microcoulombs on this equivalence capacitor. That's what came out of the battery. So the phrase you use is pretty good. It's a phrase that says, okay, that's the whole circuit. I do want to be a little careful with that phrase as we move forward, but we don't really have this circuit, right? We're trying to see how this circuit would help us with the real circuit.
Yeah.
But if you study this one carefully, the equivalent of the equivalent of the equivalent, and as you just said, this would be the 158 microcoulombs that comes out of this battery. If you take that thought back to the original real circuit, you would say 158 come out of here, 158, and it would have no other place to go but on this capacitor number 1. So I would say then I have answered, and this was the whole advantage of the equivalent of the equivalent of the equivalent. I have just put and argued that in units of microcoulombs, I would have 158 on capacitor number 1.
Is that because it's the first capacitor in the circuit?
Well, no, it's because there was no parallel path. See, I'll say it again. This is why it comes out of this battery. So coming up here, if it comes out of this battery, where does it go? It can only go here.
Yeah.
If it had come out and there was like a branch to go to another parallel capacitor, then I would have to say the total of those two is 150.
But since there's only one, like,
Yeah.
since there's only one, that's the charge of the first capacitor. But if there were
Exactly.
a parallel circuit there, you would have to figure out the different charges on
Yeah,
each.
then I would have to say the sum of the two is 150.
Okay.
Mm-hmm. So that is using the principle of conservation of charge to make that statement. Yeah.
Okay.
Okay, now let's just keep working backward, because like I said, the first half was just getting to this circuit, which is the equivalent of the equivalent of the equivalent. The second half of this is now kind of working backwards and see how these equivalents can be used to figure out what is the charge on the individual capacitors. And as you just pointed out, I was able to, oops, I just bumped my computer. Did it change anything? Oh, screen still there? My hand? Okay, good. So, and I would say so far it's done this much for me. It has helped me figure out the charge on capacitor number 1. Well, watch this. I think this could be somewhat useful. It's not the whole circuit, but if I go to this one here, which I'll call the equivalent of the equivalent, so this one here, if you look at this comes out of the battery, I would say it would be 158 microcoulombs, goes on to capacitor number 1, and then that gets chased off and can only go to this capacitor, which isn't one of our original real ones, but I would say then that I have a capacitance, a charge of 158 microcoulombs on this guy. Now, again, I'll admit that doesn't really help me with the real circuit, because when I come back to the real circuit, if 158 are coming off of capacitor number 1, and this is kind of what your question was leading to, right here, this little node is a split, and some of the charges is going to go over here to capacitor 2, and some of it is going to go to number 3. So what it does tell me is that the total charge on 2 and 3 added together is 158. It doesn't tell me them individually. So I can't really put anything in this chart, sadly, but I can say charge on number 2 plus charge on number 3 is 158. And then that, who knows, that may be useful in a little bit. But I'm kind of looking ahead. It's really not going to be that useful. But there's 2 ways to go. So if you went the harder way, it would be useful. If you go the easier way, it's not as useful.
Okay.
Okay. But here's where it can get very, very, very useful. Okay. Keep in mind, and let's see, where did I write the basic definition of capacitance somewhere? Oh, right here on top of page 2. That there is a mathematical connection between the charge, the voltage, and the capacitance. Now, I say that because if you know any 2 of these, you can get the third. So if you come back to our chart, so far I only have the charge on number 1, but that can easily give me the voltage. Because I know the capacitance and I know the charge.
Yeah.
So I know the capacitance and I know the charge, and now I can get that voltage. So that's going to be easy to get. I don't know if I should, keep moving on to the harder ones or do that easy one, but maybe I will. I can keep in mind that once I know 2 of them, I can get the third. Okay, so coming over here then, to get voltage, I would take the charge, 158 micro, and I would divide it by the capacitance, which is 15 micro, and I get 10.5 volts. Now your analogy in water can really come into play here, or our definition of capacitance. Because, let me come back to this circuit right here, which again, I will call the equivalent of the equivalent. And this is the battery, what you call the push, water pressure, if you will. It's 20 volts. These two are in series, so these are the ones that are getting that push. So these two together being in series got to add up to my 20. So that would tell me that the voltage here on this one is, hey, stopped again. I saw it that time. When do I do that?
Huh.
Maybe there's a timeout feature. You know, I did reboot my phone in the break because of all that other trouble we were having.
Your phone's live again.
Ah, good, thank you. But it's still on never. Okay. Yeah, so now I don't understand why it's disconnecting because my phone's not going to sleep.
Maybe it was just trying to catch up or something.
Yeah. Okay. So back to this, and maybe I'm taking too long on it because well, I want you to understand. So I want to go slow, but at the same time, I don't want you to think it's overwhelmingly hard. But here's what I would have done. Of course, I could say then that the voltage on this 2, 3, and 4 equivalent could be 9.5, but I think there might be even a more straightforward way of doing that. And that is, again, using this. Remember, if we know any two of these, we can find the third. And back here in the equivalent of the equivalent, we know the charge on this equivalent, and we know the capacitance. So the voltage, which would be the charge over the capacitance, could tell me this voltage. And I'm just kind of curious to see if I still get 9.5. So the charge is the 158. The equivalent capacitance is 16.67. And yeah, sure enough, I get 9.5. So
Okay.
this is 9.5. But again, I'll just keep saying it this way. That's the equivalent circuit. My question, though, is, does this equivalent one, so this is the equivalent of the equivalent, does this help me in any way over here? And I would say, yes, it does. It may not be obvious to see it, but these three are the voltage from here to here. And that change of voltage would be this step right there. You might even go back to this equivalent one, right? This one, because we said they were in parallel, had the same voltage. So this equivalent one is telling me that this is 9.5 volts across capacitor number 2. It's also 9.5 volts across the combination of 3 and 4. Now, I want to know 3 and 4 individually. So that's really not going to help me individually, but it is going to help me right there. And so what I'm getting at is for number 2, I know the voltage has to be 9.5, whether you figured it out because these two have to add to 20, or if you figured it out by taking the charge and figuring out what the voltage is and coming back to this equivalent one. Whichever way you want to do it, this is telling you the voltage on number 2 is 9.5 volts. So again, this is the whole lesson, and the trickiness of this is get the equivalents, and then maybe the equivalents of the equivalents, and in this case, the equivalent of the equivalent of the equivalents, and then start working backwards. Use each of those, knowing that they're equivalent, and of course, using the equivalents to point back to the original one and say, okay, how does that help me with the original? And so in this case, it gave me the 9.5 volts. And I would even go further now, because notice, as I said earlier, if you know any two of these, you know the third. So I would know then and be able to calculate the charge. So grabbing my calculator, if I take the capacitance, which is 10 microfarads, and I multiply by a voltage of 9.5, I would get then 95 microcoulombs. So that's, now I'm halfway done with the problem. Now I know the charge and the voltage on number 2. In fact, let's keep going, because remember back in this picture, we had said that the 158 comes off of capacitor number 1, and some of it goes to 2 and some of it goes to 3. And so what we said is the sum of them, that's what this little equation here was for. The sum of them says that the sum of these two charges is 158. And we just found that number 2 is 95. So if I take the 158 and subtract off the 95 that went on to capacitor number 2, that means the 63 is left over to go to capacitor number 3. So back in my original picture, I would be saying, okay, so there's 95 on here and 63 on there. So when I add the two together, I get the 158 that came off of capacitor number 1 and then split right here at the node, where some of it, 95 of it, went to capacitor 2 and the other 63 went to capacitor number 3. So I'm going to take advantage of that statement earlier about conservation of charge, knowing that it has to add to 158. So once I get this charge on number 2, I easily have the charge on number 3. In fact, then I'll go one step further. Remember, if I know any 2 of these, I can find the third one real easy. And so I have these 2, and I come back up to this. And so to get the voltage, I will then take the charge, that's the 63, and divide it by the capacitance of the 20 and get a 3.15 volts.
And then for the fourth capacitor, since you know that piece had 9.5 volts on it, could you just minus 3.15 from 9.5?
Yes, that's one way. I would even say there's an easier way, but that's one way. Let me take you a different way, because that's true. But I would do this, looking back at the original circuit, whatever goes on to number 3 comes off and goes into number 4, right? That's what we mean by series. So number 4 must have a charge of 63. So I can put that into here, 63. And then once I know any 2 of those, I can get this. But you said it must match the difference of those 2. So let's check. And so to get the voltage, I would take the charge, 63, and divide it by the capacitance of 10. Well, I guess I don't need a calculator for that. And get 6.3. And sure enough, these 2, well, with some rounding, add up to that one. Mm-hmm.
Okay, so because 3 and 4 are in series, they get the same charge.
Yep.
Basically.
It's the same argument that we said capacitor number 1 gets the same charge that came out of the battery.
Okay, that answers my last question on it. Cool.
And so you can see here I'm heavily using the fundamental physics principle of conservation of charge.
Cool.
And
Thank you.
And that's what I mean by saying there's kind of 2 big steps to a problem like this. The first one is to take all these 4 capacitors and get its equivalent, and then the equivalent of the equivalent, and then finally the equivalence of the equivalence of the equivalence, and see how that helps you. And you have to kind of take that one and start looking back at these other ones and seeing how does that help me, or this one and look back, and this one and look back, and eventually you'll get all the pieces to it. Nice.
Yeah, I had the main idea of how to do it. It's just I didn't know how to split up some of the pieces, but you answered those questions.
Oh, good. Hopefully I didn't make it too hard or too easy. I don't want you to make it too hard.
Your next session is at 3, right?
What do we do? Let's see, we started 12. Oh yeah, so we're getting close to 2, huh? Yeah, so the next one's at 3, yeah.
Okay, I gotta go.
Oh, okay.
I'm fixing up a car that we're trying to get ready to sell, so I gotta go work on that a little bit, and then I'll see you at 3.
All right, well, work on that wiring if it's series or parallel.
I will. All right. Thank you. Bye.
Bye now. All right. Hey, jump in line for 120. Yes, I will do a 121. Oh, then you say, never mind. I sorted it out. Okay, great. All right, then. Have a nice day. All right. Oh, yes. And, I apologize. I won't even, I'll just say B since I'll mess up your name here. 21. And you're the one who didn't have a microphone. So keep shooting stuff in the chat room if you need to. But a quick 121 conceptual question. Oh, can I share my screen? Well, yes, you can. I think I got to give you permission, though, and I know I have to stop mine. So let's see here. Stop mine. And then I don't think I gave the permission yet this time. Yeah, all participants. Okay. All right. That should do it. Go ahead. Share your screen. Oh, hey, we're just down to you and me, huh? Okay, so Becky and Juan are playing catch. Oh, let me get a new piece of paper here. And let me go 113. This is from 121. And I'll just put here Becky and Juan. All right. So Becky and Juan are playing catch on the flat ground. Okay, keep in mind that. Becky throws the ball. Let me draw a picture before I knock your screen off here. All right, so I'm going to draw a flat surface. Becky throws the ball with a specific launch speed of 10 meters per second, okay? Ignoring air resistance, how many different launch angles will allow one to catch the ball without moving? Well, I like this. And it's 2. Good, and I see that it says correct answer is number 2. That's true. As long as Becky throws it fast enough. I mean, if she doesn't throw it fast enough, it never gets to 1. So then it would be 0, but that's not an option. Okay, so 2. So let's talk about 2. I'm gonna share my screen here back and show you my camera. Oh yeah, and then I've got to reconnect my camera. Here we go. Nice. Okay. There's a couple ways, depending on how much you might have remembered. Maybe I'll just start from scratch. But if we put a B here for Becky and a J here for Juan, one of the things in our two-dimensional motion is the object will follow a parabola. And in this case, and this is the point of the problem, we can show that there are 2 parabolas for a given launch speed that will get there. And it goes something like this. I like to make 2 columns when I do two-dimensional stuff so that I can kind of keep track, because the whole idea is that the X motion behaves different than the Y motion. Okay, so if we wrote out a formula for something moving in the X, it might look something like this. And the throwing position, let's call that 0. The initial velocity in the X direction, so let me just kind of use this lower one. Let's say Becky throws it at some angle theta. There would be then the throwing speed V0 times cosine of theta times t. And there's no acceleration in the X direction. So the equation describing where the ball is in the x is given by this equation for a given initial speed and a given angle. And then for the y motion, if we write out the basic equation for starters here and apply it to this little projectile, we might say, okay, let's say it again launched from position 0. The initial speed in the y direction then would be the speed that Becky throws it times the sine of the angle times t. And the acceleration in the y direction is a negative 9.8. And so we like to use the symbol g for 9.8. So that's the g here, or the negative g. So there's the 2, and then there's the t squared. Now, the real key to this problem is to say that since Becky and Juan are on the same level, Juan is going to catch it at a position 0. So I will say that if I put in y equals to 0, we are talking about the time it would take to get to 1. Which by extension, if I come back to the x direction and we say that 1 is a distance of r, we often use the r for the range, then we're saying for this time, that solves this equation right here, that time put into here would tell us how far 1 is. Okay. Now, this question is not about the time, so I'm going to eliminate that by doing this. I'm going to write this as r over v naught cosine squared t equals to t. And I'm going to put that up here into the y motion. And so if r represents the range, then t represents how long it took to get to 1. Which is exactly what I want here, the time it takes to get back to 0, which is the vertical position of 1. So I'll put a v naught sine theta, and then in place of t, I'll put the range, r, over v naught. Oh, why did I put a square? I was thinking ahead here. I'm going to square it eventually, but I didn't mean to do that quite yet. All right, so this would be cosine theta. And then this is minus g over 2. And then there's the squared. So there'd be an r squared. There'd be a v naught squared. And there'd be a cosine squared. Okay. Now, if we simplify this, 0 equals, the v naughts cancel off. Sine over cosine makes a tangent. And then I'll put an r minus, and I'll put a g and an r squared over 2 v naught squared. And here's going to be kind of this magical piece here. Solving equations with trig functions can be a little mathematically challenging. And so you want to make sure you have the same functions. So like here I have sines and cosines. That's not useful. Together I convert it into a tangent. But then over here I have a cosine, which the cosine with the tangent is not helpful. So I need to write them all as the same trig function, either all as sines or all as cosines for this to be useful. And fortunately, if you remember one of your trig identities, it's called the Pythagorean Identity, says that a sine squared plus a cosine squared equals 1. So if you start there and divide everything by cosine squared, on the right-hand side, I get 1 over cosine squared. That's exactly what that term is. It's a 1 over a cosine squared. What does it equal? Well, on this side, this is a +1, and this first term is now a tangent squared. So this is referred to as another one of the Pythagorean identities for trig. So you can put that into here. Cosine, tangent squared +1. All right, let me call that page 1. So then, if I move on here and start to simplify this a little bit, and I guess I can't go too far, although I guess I could factor out an r and divide by 0, so it goes away. I have a tangent. I then would have a minus gr over 2 v naught tangent squared of theta. Then would have a minus a g and an r, and then a 2 v naught squared. And if I do one more step, you can kind of see it here, a g, an r, over a 2 v naught, I think that was supposed to be a squared, tangent squared, when I move this to the other side of the equation. If I move this to the other side of the equation, it's minus tangent. And if I move this to the other side, it becomes a plus gr over 2 v naught. And I guess I didn't have to move them to the other side. I just kind of like the positives to be in front of the quadratic term. But if you think of this as a u, and so this is a u squared, so we'll do kind of a, what you call a u sub. Now, not a trig u sub, not a calculus u sub, but a u sub in terms of the variables. You can maybe now see, even though you're not asked to actually solve this, there would be 2 solutions, because this is a quadratic equation. And normally, in a quadratic equation, we write the coefficient in front of the square as a, the coefficient in front of the linear term is b, and this as c. So if you think of this as a u squared minus a b, which is just 1 u, plus a c, actually maybe I should just write it as plus b, and so we'll call b a -1. You've got the standard form for a quadratic equation. And so that means u equals plus or minus, well, minus b, plus or minus the square root of b squared minus 4ac all over 2a. And I'm going way beyond what the problem requires. If they gave us some numbers, we could actually then solve. If they had given us, well, we know b is -1, but if they had given us how far wand is, that's the range, and we know that's 9.8, and we give it how much Becky threw it, we could get then a, and we could also get c, and we could actually then get tangent theta, because that's what u is, and there'd be 2 answers. There would be a plus and a minus. And so if you use the plus sign, you would get a theta with plus sign. But you would also get a theta with a minus sign. And that's how you can do that. All right. Okay. Can they answer this question intuitively? Yeah. You can answer it intuitively. Sort of. I mean, you would have to go through this at one point. And I think your book did. I'm quite sure it did, because if you study this, you will see with a trig identity that the 2 angles, so let me call this answer 1 and answer 2, theta 1 and theta 2 have to add up to 90 degrees. And you can see that intuitively, because back here when you're writing out the equations, if these switched roles, if they added to 90 degrees, remember they complement each other. That's why they're called complementary angles. And so they would switch roles and they would have the same solution. So if it worked out that answer number 1 was 30 degrees, then answer number 2 is 60 degrees. That would be a little bit easier to see had I solved this a little differently. How are we on time? Oh, well. Okay, well, if you're good with that, but I would say this: if I had solved this for r equals, and I left the way back here v naught cosine theta, and instead of solving this for time and putting it into here, if I had solved this one for time and put it into here, watch what happens. And I probably should have, because I think that's a little easier to see. I would have a 0 here. I would factor out a time, and I'll do that kind of quickly. But when something equals 0, that means either this one equals 0 or this one equals 0. Now, 0 time would be when the ball is being thrown by Becky. So the other time is the one we want. And so I would try to solve this. I would say v naught sine theta would equal then to be gt over 2. Move the 2 over. Move the g downstairs, and that would be t. So when I put it over to here, I'd get 2 v naught sine theta over g. And the reason I think this math is a little easier to see, it's still not really intuitive, but it's a little easier to see because you'd have 2 v naught squared. And here's the magical piece. You would have cosine theta times sine theta over g. And so remember, these are complementary. And so cosine of 30 times sine of 60 would definitely then be the same thing as cosine of 60 and sine of 30. And so long as these two angles add up to 90, I'm sorry. Sorry, I said that totally wrong. If you put in 30 degrees, you get something like this. And then in the other angle, which would be 60 degrees, would actually come out to be the same thing, because the cosine of 30 is the same as the sine of 60, and the sine of 30 is the same as the cosine of 60. And that's true as long as the two angles add up to 90. So that's where you can see that there would be two answers that have to add up to 90. So maybe that would be have been a better way to do it. Not sure. But I will see you in 50 minutes if you're around for the next session. But yeah, the answer is definitely 2. And I'll say it again, as long as, and that's key, as long as at least Becky threw it hard enough to get there, because it could be no answers. It could be 0. It could be something that looked maybe more like this, that Becky throws it and it goes plop and plop. So if you don't throw it hard enough, or with enough angle. So whatever the angle is, then there's 2, but there could be no solutions. Like you could just throw it, straight, let's say, and it falls long before it gets to 1. And then the complement to that is straight up, and it just goes straight up out of Becky and goes straight down and never gets to 1. So could be 2, could be 0, but it can't be a 1 or a 3 or a 4. All right, I'll see you a little later. Take care.